Alright, this is online class 16. Here we're going to cover section 8.4 in our text, and we're going to be testing a claim about a population mean mu with the agreement that sigma is known for this section, much like it was in section 7.3, I believe it was. Right? Alright. Again, we've got a big population. Alright, and let's say some big population, we're interested in some numerical measurement of interest, and there is some population mean regarding this numerical measurement that typically we will never know. Alright, somebody makes a claim, or let's say the historically accepted claim is that the population mean equals some value, and let's say some challenger emerges based on some sample data. Perhaps we notice that some sample means are coming up that disagree with this H0 assumption, and we can challenge that claim with an alternative claim that would take on one of these three forms. Either mu is greater than the traditionally observed value, mu is less than that value, or mu is not equal to that value. So much like we did in section 8.3, we're going to test these claims. We're going to test the null claim versus the H1 claim. Who's going to win? Well, that's to be determined, and we're going to perform this test with our sample mean. Okay, basically we draw a sample, we observe what it is, and we compute a p-value like in 8.3 to test these claims. Okay, oops, what happened there? Hang on a minute. Okay. Alright, a sample mean will yield a z-score. As we know, the central limit theorem tells us sample means are normally distributed with the mean that equals the population mean and a standard deviation that equals the population SD divided by the square root of the sample size. Alright. Well, the calculator in this context at least will compute this for us. The sample mean will give us a z-value, and the z-value will lead to a p-value. Again, the calculator computes this all upstream, and based on the p-value, much like in section 8.3, we either reject the null claim or fail to reject the null claim. Almost ran out of room there. Okay. Alright, so since we've already had a face-to-face class examining the structure of this hypothesis test procedure as in 8.3, I'm going to jump right in and do an example. It's in our homework list. It's number 6 on page 430. So take a minute to familiarize yourself with that example, with that homework exercise, and come back when you're ready. Oh, I'm sorry, it's number 7. Please forgive me. I hope I didn't lose you there. Number 7 on page 430. All right. Writing a hit song in the manual. How to have a number 1 the easy way. It is stated that a song must be no longer than 3 minutes and 30 seconds or 210 seconds. A simple random sample of 40 current hit songs results in a mean length of 252.5 seconds. Alright, basically what's going on here. Let's in wide strokes inform ourselves of what the given information is. And I'm having a little trouble here today with the screen wandering. Alright, basically we're taking a sample of 40 hit songs. Right? From those 40 current hit songs, the mean length is 252.5 in seconds. Alright, we're going to assume the population standard deviation for the time length of all hit songs is 54.5 seconds. The book tells us to use a 0.05 level of significance, or significance level, to test the claim. Alright, do you hear the bells? Test what claim? That the sample is from a population of songs with a mean greater than 210. A population mean greater than 210. Alright, that is a claim about the population mean. I'm going to call that the alternative claim, or the alternative hypothesis, because it's an inequality. By implication, the null hypothesis is that mu, the population mean for song lengths, is 210 seconds. Alright, well, the idea here is we've got a sample mean that appears to be higher than the assumed value of 210 seconds. Now the idea here is clearly the population mean, the assumed population mean is 210. The sample mean is running a little higher, at least in this sample. Is this difference statistically significant? That's what the p-value is going to tell us. Right? So I'm going to test this hypothesis. Does this sample mean value lead us to want to embrace this new claim? Well, we'll have to see. Alright, so we're going to compute the p-value of our sample data. And as you may recall, just like in section 8.3, the calculator takes a lot of the drudgery out of this for us. In section 8.4, we're going to use a new test on our calculator. It's called the z-test operator. And again, that makes the assumption that sigma is known. You'll even see it on the calculator entry pad. That sigma is assumed to be known. It asks you, prompts you for what sigma is. Alright, how do you get there? Well, as you probably can figure out from last time, you press the stat button, then the test button. And we're going to be using a new command here, the z-test command, not z-interval, but z-test. And it's number 1 on this list. Alright, you'll see the input screen looks very familiar. It should look very familiar to us. And let me sketch it out here. Our input, again, we're going to use summary statistics mode. The data mode we'll save perhaps for a face-to-face class. Right, just highlight and select the stats input mode if it's not already selected. The calculator then prompts you for mu sub 0. Again, this is the Texas Instruments code for the null hypothesis. Alright, so mu sub 0, well, that's equivalent to h sub 0 equaling 210, so I'll enter in 210. Notice the calculator then prompts us for a sigma. So the calculator agrees with us if we're going to use the z-test command that we have to know the population standard deviation, or we make some assumption that it is known. The sample mean is 252.5 and the sample size is 40 in this problem. Alright, now it's critical you pick the right test here. They're saying, well, what's the challenger? Well, are we claiming that mu is not equal to, greater than, or less than 210? Well, as we saw above, let me scroll up there. the sign, the inequality symbol in H1 will determine what type of test it is, either right-tailed, two-tailed, or left-tailed. Alright, so we'll want to pick, of course, the greater than mu sub 0 option, indicating it's a right-tailed test. Alright, so then we select or highlight and select calculate. And on the resulting screen output, well, let me summarize it here. First time out with this command. You should see z-test at the heading. Again, much like in 8.3, the alternative hypothesis comes up on the screen. All right, the z-value of our test statistic, our test data, comes up. But I'm more interested in the p-value, which is, I'm going to summarize as 4.07 e to the minus 7th power. Of course, this is scientific notation. This is Texas Instruments syntax for scientific notation. It's 4.07 times 10 to the minus 7th. I mean, it's a very small positive number, very close to 0. Alright, so this is my p-value. And really, it's 407 with 6 decimal places in front of it. A very, very, very small positive number, right? Alright, and again, much like section 8.3, now we will compare. Compare the p-value to your alpha level, which is typically given to you in the problem statement. Whoops. I'm going to call 4.07 times 10 to the minus 7th power a very small positive number. I'm just going to call it 0 plus, because all I need to determine is if p-value is less than or greater than alpha, right? My alpha level stated in this problem was 0.05, and of course, in this problem, your p-value is going to be less than any reasonably chosen alpha level or significance level. So my claim here now is to reject H0. And I should probably specify the significance level. In theory, your significance level choice might change your conclusion. Probably not in this problem. Alright? Alright, the book asks us to interpret, and I might, well, let me see. Let me read what the book says here. This is for number 7. There is sufficient evidence to support the claim that the sample is from a population of songs with a mean length greater than 210. Alright, well, remember, what did H0 say? We're rejecting H0. H0 said that the mean was 210. Alright, if we're rejecting H0, we're saying that our sample data indicates, our sample mean in this problem indicates that perhaps this is false, perhaps no longer true. Maybe songs are getting longer in length as we enter in a modern recording age. Alright, so I might summarize it like this. I'll say sample evidence is statistically significant in suggesting the population mean length of all songs is greater than 210 in seconds. Okay. Alright, so again, much like we did in section 8.3, very similar command. The framework is very similar, but again, we're testing claims about something else now. We're testing claims about population mean in section 8.4. Okay? Alright, let me give you a screen here. I want to do another homework example. I want to do a a right-tailed, a left-tailed, and a two-tailed test before we call it a day. And we already did a right-tailed test. Alright. A minute here. Here we go. Alright, I want to talk about the next problem in the homework list, and that's number 8 on page 430. And let me check because I made a little mistake last time. Yes, number 8 on page 430. Please familiarize yourself with that problem and come back when you're ready. Please pause now. Alright. A simple random sample of 50 adults. I'm going to start writing some information down right here. So we're going to take a sample of 50 adults, and each person's red blood cell count in cells per microliter is measured. The sample mean for the red blood cell count is 5.23 in cells per microliter. It's a millionth of a liter. The population standard deviation for red blood cell counts is 0.54. Now again, in section 8.4, we're making the assumption that sigma is known. Alright, so 0.54. Use a 0.01 significance level to test the claim. Here we go. That the sample is from a population with a mean less than 5.4. Population mean less than 5.4. Okay? Which is a value often used, etc., etc. What do the results suggest about the sample group? Alright, so somebody's making this claim that the population mean for red blood cell counts is less than 5.4, where the historically assumed value has been that mu equals 5.4. Again, let's take a bird's eye view here. If we look at our sample mean, it is clearly less than the historically assumed value of 5.4. Hope you agree. The idea is this difference statistically significant. Or is this difference significantly less than 5.4, since we're talking about a left-tailed test? Let me write that down. Left-tailed test. And as usual, the symbol in H1 determines the type of test. Okay? Alright, so step 1 is done. Remember, step 1 is to state the hypotheses. Step 2 is to compute the p-value. The p-value tells it all. Alright, so again, we're going to go to our z-test command. In section 8.4, press your stat button, then tests, then z-test. It's on the very top. I suppose I'll write this all out again. For your input, you want to select the statistical summary mode. Let's see. The population mean, the null hypothesis is going to be the claim that the sample mean is 5.4, right? The sample mean will enter as 5.23. Oh, sorry, I made a mistake here. Let me go back. Alright, the next item on the menu is the population standard deviation, which is 0.54. The sample mean is 5.23. And again, the sample size is 50. Again, we want to pick the left tail test here. We're worried about being less than the historically assumed claim. And if we go through that process, hit highlight calculate and select, we'll get a p-value of 0.013 from this sample data. Alright, now again, I like to make this little mini table. We're going to compare. This is step 3, is to compare your p-value to your alpha level. And I like to do it just like this. Write down my p-value, 0.013, and right under that p-value and my alpha notation, I'm going to select the alpha notation. Let me check. And let's see, they wanted you to have a 0.01 significance level. Okay? Let me double check it. Use a 0.01 significance level. Alright, so my p-value is greater than alpha. Not by a whole lot, but it is greater than. So now we make our conclusion. When your p-value is greater than alpha, you fail to reject H0. In other words, remember, small p-values suggest H0 is false. Large p-values suggest H0 is true. How large? Larger than alpha. Okay? So this is my conclusion. For this hypothesis test, fail to reject H0. Basically, this is saying my sample data was weak in trying to make the claim that the population mean was indeed less than 5.4. How do we interpret this statement? Well, let me read you the author's answer. There is not sufficient evidence to support the claim that the sample is from a population with a mean less than 5.4. So let me write that down. Not sufficient evidence to support the claim that the sample is from a population mean less than 5.4. Let me just kind of abbreviate that the population mean okay. In other words, that difference that we originally saw between the sample mean and the population mean, the assumed population mean, was not statistically significant. I suppose that's another way to say it, okay? Alright, so we did a right tail test, we just completed a left tail test, and now I want to talk about a two tail test. I don't think I'm going to need another screen here. Let me try to put this on the same screen. And I want to talk about number 10. This is going to be number 10 on the same page, page 430 in your text. Let me check it. Number 10, human body temperature, and page 430. So please read that problem, familiarize yourself with the problem, and come back when you're ready. Alright. Number 10, human body temperature. Data set 2 in Appendix B includes a sample of 106 body temperatures with a mean. Now this is going to be a sample mean of 98.2. Assume that sigma, the population standard deviation of body temperatures, is known to be 0.62 in degrees Fahrenheit. Use a 0.05 significance level to test the claim that the mean body temperature of the population is equal to 98.6. The population mean is equal to 98.6. Alright, so we're going to test this claim with our sample data. Again, let me take a bird's eye view here. That is our sample mean temperature. This is our assumed population mean temperature. They do not agree. The sample mean is less than the population mean. Is this difference statistically significant? Well, that's what we're going to find out. Again, the convention is if you're testing a claim that has an equality, we by default call that the null hypothesis. So I label that H sub 0, and H1 is then going to be that mu is not equal to 98.6. And it's the assumption is that mu is, and H1 has to be that mu isn't. And again, we're going to be in this two-tailed test, we're going to be worried about being high or low. And that just translates into making the right selection on your TI calculator. Alright, step 1 is done. We state the hypothesis. Step 2, find the p-value. Again, you go to your TI 83 or 84, we'll press stat, then tests on the submenu, then select z-test. You're doing a z-based hypothesis test here. Alright, the calculator asks us for the null hypothesis. Well, the null hypothesis says that mu has to be 98.6, okay? The population standard deviation is 0.62. We'll enter that in. The sample mean we get is 98.2 in degrees Fahrenheit. The sample size is 106. And again, critical that you pick the right type of test here. Because H0 is given as an equality, we have to assume that H1 is then a strict inequality, not equal to mu sub 0. So be sure to pick the corresponding right type of test. Alright, I won't write down all the details here since we've already been through this twice. From the results screen, we get a p-value of 3.1 times 10 to the minus 11th power. And again, for practical purposes, I'm going to say that's a very small positive number. It's basically a 3 and a 1 with 10 decimal places before it. So again, I make my little mini table here. Okay, so this is step 2 is now done. Step 3 is to compare your p-value to your alpha level. As you might expect, if at any reasonable choice of alpha, I'm going to claim p-value is less. Let's see, in number 10, refresh my memory here. It's up on the screen. Let's see, use a 0.05 significance level. And of course, your p-value is going to be less than alpha here. And we're ready for our conclusion. Again, small p-values suggest H0 is true. I'm sorry, oh boy. Small p-values suggest H0 is false. Let me write that down. Small p-values suggest H0 is false, right? How small? Smaller than alpha. Alpha is the bar that you've got to overcome to reject H0. So I claim we reject H0 at alpha equals 0.05, again at any reasonable choice of significance level. This is going to be my conclusion. Alright. The book asks us, so the book in these homework problems, they tend to ask us for some sort of interpretive statement at the end of all these problems. Let me see what it says here. 98.6 degrees Fahrenheit is commonly believed as a population mean temperature. Is there sufficient evidence to conclude that the common belief is wrong? And our author states, there is sufficient evidence to warrant rejection of the claim that the mean body temperature is 98.6. Alright, so what I'm going to say is based on this data. Interpret. Based on this data, I'll say there is sufficient evidence to support the claim that the population mean temperature is not 98.6 in degrees Fahrenheit as is somewhat commonly believed. Okay? The author has a comment here. I'm just reading out of my book. There is sufficient evidence to conclude that the common belief is wrong. Okay? Alright, we were at the 32-minute point, so I'm going to call it a day. And this concludes Online Class 16, Section 8.4, testing claims about a population mean. That is all.